That's beautiful. Okay. Scientists, how are you? Good. All right. Very good. This is Chemistry 1P. So if you don't want to hear about chemistry, then it's your time to get up. Run out the door and sit in the park and enjoy yourself. We'll be enjoying ourselves right here. And I'll be assisting you in this first lecture. And I'm going to point out a couple of important administrative points for this next quarter regarding this class. All right, so let me first, whoa, there's a lot of interesting, oh, that's, I want to introduce your instructor. So unfortunately not this guy, also not this guy, but it's myself. I changed a little bit over the years. I was about 4 years old, I guess. Still have a sweater though. This is my email address. Don't abuse it, okay? And this is where I live. So meet me, that's where I am. I do have office hours. Well, let me lower the volume a little bit. This is really, really, really cool. Let's see. I think this is better. I have office hours on Mondays and Wednesdays in the morning, 9 o'clock, so you're welcome to walk into my office and ask me questions. And you won't be doing that probably on Monday directly, but when the quarter evolves, it's a good thing to stay in contact and ask me questions directly in case you're not sure about anything that's going on in the course. Okay, so what are we going to talk about? This is Chemistry 1P. It's an introduction class to chemistry. It covers a whole bunch of things about chemistry that we need to know before we're going to start the Chemistry 1A series, 1A, B, and C. Okay, so this class really prepares you for that. Gives you a lot of information, and after this you should be ready to basically dive into the Chemistry 1A, B, and C series. So we'll start with some general things, talking about numbers and units. Chemistry is one of the natural sciences, and we will be using some very practical calculations. You have to do those correctly. So we need to be able to work with numbers and units. And most of this you already know, but I just want to make sure that you can do this and we speak the same language. Atoms and ions, of course, those are the key building blocks. This is the thing that defines chemistry, atoms and ions, and molecules. So we're introducing these, point out the differences, and point out the general architecture of each of them. Then we'll have actually a midterm, and after the midterm, we start talking about atomic mass, mass calculations, and stoichiometry. So again, we'll be using chemical concepts, doing calculations, and trying to solve some chemical problems. And then finally, after the second midterm, which is a little late in the season, unfortunately. I can't help it because it kind of coincides with Thanksgiving holidays, and so we have to push it up to November 30th. So it's a little late in the season, but you know, again, I can't help it. I apologize for that in advance. Finally, after the second midterm, we'll be looking at several chemical reactions, doing chemical calculations with them. And again, trying to solve some chemical problems. Okay, so by the end of this ride, you should be ready to take on some very basic and general chemistry problems. Okay, so let's start with, we're going to top off this lecture. This is a lecture probably a little bit on the short side of things. I'm going to introduce concept of chemistry in the next couple of slides. Okay, what is matter? That's an important question because chemistry deals with matter. Chemistry is a science that looks at matter and is trying to understand why is matter the way it is. Can we understand that? And can we do something useful with it? Okay? That's what we're trying to do in chemistry. So this is Earth. Okay? If you like it or not, you are on this planet. And if you zoom in a little bit, you see here, this is Southern California, right? You might recognize this. This is a very interesting day because look at all these wildfires. Pretty dramatic. So we're somewhere right, this is kind of Los Angeles, Orange County right here. Let's zoom in. Oops! This is LA. So why do I show this? Because basically, I mean, the planet is made of materials, right? California is made of materials, the water, the landmass. Los Angeles is made of materials. All these buildings are made of things. You can touch it, you can hold it. That is stuff. That stuff is materials, right? And chemistry has something to say about those things. So let's go in a little further. This is Santa Monica, 2 people here. We're diving into these people. Boom! Into their bodies. And we see things like this. These are cells, right? You know that. I don't have to tell you anything. But these cells, of course, are composed of stuff. This stuff are materials. And these materials are composed of even smaller structures than this. So if we zoom in even more, we find proteins, for instance. This is one big protein. Every little color here is an individual atom. And this whole thing is a molecule. And this is the level where chemistry is trying to say something interesting. Right? This is the level where chemistry is trying to make connections and try to understand why certain molecules behave in a certain way, why material feels soft or hard. Okay? So it all comes from the molecular perspective. That's what chemists do. So if we zoom in even more, we see something like this. You see individual atoms here, an ion, calcium ion, in the protein, and then the very basic building block in chemistry is the atom. Okay? The atom is fundamental building block that we deal with in chemistry. This looks atom-esque, okay? Atom-like. But this is not necessarily true. This is just a rendering by an artist that went off, okay? Because this is not something that I would recommend as an atom. And we'll talk about that a little bit more in detail during one of the lectures. Okay, so let's see. How should we think about an atom? What does it really look like? Or can we say something sensible about the way it looks? One thing I can tell you that these atoms, this is very important, are absolutely real. Okay? I say this because some people think that they're just some kind of abstract notions. Okay? Something that the chemistry teacher made up. The world is made out of atoms. But since you are much bigger than atoms, you will never see one. So if you never see one, how can you be sure that they are actually there? It could be just some kind of theoretical framework that we're talking about. The answer is, it's not. It's very real. Very real. We can see atoms not with our own eyes, but with, I would say, advanced instrumentation. Okay, so this is a very wonderful image taken by a scanning tunneling microscope. It's a very advanced instrument that can literally feel where atoms are. And they can see what is the shape of an atom. How big is it? Where is it? Is it there or is it there? Right? So this actually indicates that atoms are real things. They have a mass. They can lie here or there. You can pick it up and put it somewhere else. These are real things. These humps here are actually ions in a lattice of sodium chloride. Okay? They're visualized by this microscope. Every bump is an individual ion, an individual particle. Okay, they're real, but why is it sometimes hard to comprehend what kinds of issues that have to deal with atoms? The reason is because they're small. Atoms are very small. And so it just is excessively hard to analyze them, to try to understand how they behave. You need to have very sophisticated tools to do that, and that is not easy. Now, how big are these atoms, actually? It's good to know. We have a sense of how big atoms are. So let's take this little grain of salt. You probably know the size of an individual grain of salt. Okay? So that's about 0.5 millimeter. And this is a metric unit you may or may not be familiar with. You can also say it's about 1/50th of an inch, okay, the size of a single grain of salt. Now, if we take one of these guys, let's say this guy, and shrink it by 10 million times, then you arrive at the level of an atom. This is the world in which atoms live, on the 150 picometer scale. That's the size of an individual atom. This is a hydrogen atom. Okay, you might say, well, 10 million is a big number. number, but it's not an inconceivably big number. It is a number that you may comprehend. Okay? You, not me, may have $10 million on your bank account. Okay? That's a lot. But you can still comprehend the quantity. The number 10 million is not a number that's out of our reach. Our brain can comprehend that. So take this, take that number that you can comprehend, and then think about an atom. An atom is small, but it is not inconceivably small. So don't think that an atom is so small that you cannot say anything sensible about it. That's not true. These things are real, they have a size, they have a weight, or mass, I should say. And so there's a finiteness to that. Okay, so if you don't like this example, this is another example. Earth again, my favorite planet. And the diameter is about 13 times 10 to the 6th meter. Okay? Or for you folks that can deal with the metric system, and we'll change that. 8,000 miles is the diameter of Earth. If you take that and you shrink it by the same number, what is the size about? Take a guess. What is about the size? If I shrink Earth by 10 million times, is that like the size of a tennis ball, a marble, a car? What do you think? It's the size of a bouncy ball, okay? 1 meter size bouncy ball. So take Earth, you can probably understand how big Earth is. Shrink that thing to a bouncy ball, you see? You have the same kind of shrinking dimensions as the one up here. Now, a bouncy ball, you can completely understand how big it is. It's finite. It has a mass. You put it from here to there. Same is true with atoms. Just a lot smaller. But not inconceivably small. Okay. Now these atoms come in a whole variety of different flavors, and we will talk about them in this class. And they're ordered in this beautiful table called the periodic table. Look, there's one right there, and right there too. They're always with you here to keep you company. These elements are ordered in this fashion, and we will learn a little bit about why are they ordered in this fashion. This is not happenstance. They're ordered like this for a particular reason, and the reason why is utterly beautiful. And you will see how it works. It also tells you something about the basic architecture of the atom, why the atom looks the way it looks, as we understand it, and why their properties are different from their neighbors. Okay? So this is calcium, this is scandium. They're neighbors, but they're very different. Okay? They have different properties. And we can understand a little bit about those properties. Okay? So knowing the basics about atoms allows you to understand differences between atoms and why some atoms are very reactive, other ones are not. And this is the basis for understanding materials, and that's the basis of chemistry. Now, why should you care? Well, atoms, like I said, are the building blocks of materials all around us. This molecule, for instance, is a composite of 1, 2, 3 atoms smushed together. They're bonded. This is CO2, very important molecule in our atmosphere. This is a protein, which is also a molecule made out of atoms. A lot of linkages here. Every little sphere is an individual atom. This is a giant molecule. This is a molecule, this too. This one, of course, enlarged relative to this guy, because this sphere is as big as this. Okay? So 2 different molecules, completely different size, but they're both molecules, they're both made out of atoms. And of course, everything around us is made out of atoms. Your body, your chair you're sitting on, this table, everything. Even me, I'm also made out of atoms. Okay? And it's all around us. You cannot escape chemistry. It's just literally everywhere. Here's some cleaning supplies. Look at this molecule here. This is the quintessential detergent. And this is a way in which we will draw the molecules. You'll learn what this little squiggly thing means. Okay? This is a line structure. And this particular molecule here, from the structure itself, we can already predict how this molecule will behave. Okay? We'll see more about that. This is a soap molecule, a detergent molecule, for good reasons. Aspirin is a molecule. Okay? If you take an aspirin or any other painkiller, there's a molecule you're putting in your body. A molecule does something, goes somewhere, clicks somewhere on receptors in your brain and in your neurons, and it's changing things in your body in such a way that you don't feel pain as much. But the molecule is doing the work. And the structure of the molecule is related to why it does what it does in your body. So looking at the structure, the geometry, the location of particular bonds is the key towards understanding why this molecule behaves like a painkiller and not like a killer. Okay? Because sometimes a small little change anywhere here can basically put your belly on. Bob Marley knows everything about chemistry. This molecule is in his little cigarette, okay, and makes him feel also very happy about himself. So this molecule does something particular in the brain, and its structure, its chemical structure, defines its workings. Okay? So knowing that enables you to leverage this. Okay? You can make changes to the molecule, you can maybe do something else, or you can try to understand how some people get sick, some people get not. So this is really fundamental knowledge about everything around us. Another example. If you remember this, big explosion in the Gulf of Mexico, not very pretty, and the release of these molecules, very simple molecules, just some carbons and hydrogens, okay? Carbohydrate, hydrocarbon, I should say. And these molecules are basically the basis of gasoline. And they don't mix well with water for good reasons. And because of that, it actually introduces a lot of problems. Right? So knowing about these molecules will help you estimate what the situation is, whether there's a very risky situation or not. You need to know the chemistry of these things. Otherwise, whatever you say is just nonsense. Okay? Just a guess. You have to know the chemistry to predict why things are bad or good. Another example, which I think is the last, is green energy. This is the structural formula of cellulose. Much more complicated, as you can see. Again, a molecular structure. Atoms come together to form a structure of a particular nature which gives this material its unique properties. Okay, so I think you understand the message here I'm trying to convey. So chemistry 1P is talking about all these things, is trying to fill in the blanks about things you may not know about molecules and atoms, and how to do calculations with them, how to estimate how much you have of something, how much you will need of something to react with something else. So these are very basic ingredients of chemistry and science, and we will learn about them. We'll learn about them also because this is very important, not just for you if you want to be a chemist. Most of you may not want to be a chemist. Okay? A lot of people actually want to be a doctor or an engineer. Now, you need to know this too, right? Because as an engineer, you work with materials, you need to know why certain things behave in a certain way. If you are a doctor, you need to know how to make a buffer and how to dose your medicines to your patients. If you make a small calculation mistake, and I have wonderful examples of that, you may just kill your patient. Right? This is not a joke. This is essential information, essential skills that we're trying to convey to you here. All right, that's it. I'm done. Thank you.